All right, welcome back. It's what I call the Lesson 7.4 supplement. We're going to talk about the idea of calculating arc length. If you're using the book, this actually is in Lesson 8.1. It's one of the three topics in 8.1, but I've decided to try to expand it and kind of show you where this formula comes from. Okay, so this is another application of integrals, and the key idea with looking at arc length is I'm really trying to find the length of a curve. Okay, the length of a curve. Now, in order to do that, what I can do is actually break the curve into subintervals and actually approximate the length of each of those line segments. So if you look at the first one here, I've got one line segment. That's a okay approximation, right? But if I break it up into two different parts, that's a better approximation for the approximate length of the curve. Don't you agree? But if I broke it up into three pieces, or four pieces, or five pieces, you'll see that my approximation actually gets better and better and better. Okay? Now, the length of the line segment, which I call L, used to approximate this arc, is really just the sum of all the approximate lengths of all these small parts. So let's define it as the following. I'm going to use this notation. Bar, or the absolute value, is pi minus 1 pi. Now this just represents the length of each one of those small line segments. S-E-G. Can't spell that very well. M-E-N-T-S. And I said we have to take each of those lengths, and then what do? We add them all up. So I'm going to sum up all of the lengths from I equals 1 to n. And then that would be called the arc length, or the length of the line segment. Okay? But to get an accurate answer using the ideas of calculus here, we need to have what? We need to have a whole bunch of small line segments. How many? Well, we need to have n approach the idea of infinity. So really, L should be equal to the limit of n approach to infinity of the sum of I equals 1 to n of the length of each of those line segments. Okay? Now, in order for us to do this, we can derive an integral formula for L in the case where f is a continuous derivative. Now, let us understand once again that this absolute value of pi minus 1 times p of I, or not times p of I, like pi, right? This is actually just the distance between 2 points. And I hope you remember how to find the distance between 2 points from grade 10 math, pre-calculus. Got 2 points, x1, y1, x2, y2. The distance is, yeah, just Pythagoras if you think about it. Yeah, x sub 2 minus x sub 1 all squared plus y sub 2 minus y sub 1 all squared, and then the square root. Now, maybe that's a little bit more complicated than we need it to be, so why don't I just call the delta x sub 2 minus x sub 1 just delta x, right? The change in the x. And then y sub 2 minus y sub 1 just the delta y, or the change in the y. Okay? This is going to come in handy in a moment. Okay. Now, I also want you to apply the mean value theorem to f on this particular interval where x is from I minus 1 to x sub I. We find that there is going to be a number x sub I star, or sometimes I used to call this thing the letter c, okay? Such that in this interval, remember what mean value theorem said? You got it. A rock equals to I rock. The average rate of change equals to the instantaneous rate of change at some value c. So A rock, once again, is f of the x of I minus f of x of I minus 1 all over x of I minus x of I minus 1, right? The rate of change of the slope of the secant line. And the IROC is the instantaneous rate change for the derivative at the value of c, which I use now, x of I star. Okay? Now this is an interesting equation, but I don't like having that denominator on the left-hand side. So I'm going to ask you to multiply both sides by this to get this lovely equation. F of x of I minus f of x of I minus 1 equals to f prime of x of I star, that c value, times x of I minus x of I minus 1. Now, I hope you can see that this part on the left is really just the change in the y value. And that this x sub I minus x sub I minus 1 is really the change in the x value. So therefore, we have this equation now that delta y, the change in y, is equal to the derivative at that point c, so f prime of x sub I star multiplied by delta x. So why is this important? Well, because now I can use this idea as the distance, and I'm going to rewrite the formula. So I'm going to say p sub I minus 1 p sub I is now equal to the square root of delta x all squared. And instead of having delta y all squared, I'm going to replace delta y with what I just had in the previous line. F prime of x sub I star times delta x. And notice that this square will apply to both of these terms. And notice how there's an x delta x all squared. I can actually factor that out now. So delta x all squared, because it's in both terms, it's here and here. And if I factor that out, look what's left over. I have a 1, and I have a f prime of x of I star, and of course this whole thing is squared. Now this is kind of interesting because I can now take out this part, the square root of delta x all squared. Well, that's just delta x, and I'm going to put that at the end. So I'm going to rewrite this as 1 plus f prime of x of I star all squared, and then that delta x is now out here, delta x. So this is another way of writing the distance between those 2 points. That really short, small line segment. And remember how I said earlier that I needed L to be the limit of the sum of all those small line segments? So instead of me saying the limit as n approach to infinity of the sum of that absolute value business of p sub I minus 1 minus p sub I, I'm going to replace that with what I just have up here. So this now becomes the square root of 1 plus f prime of x sub I star all squared times delta x. And I think we've seen something like this before, haven't we? And we looked at the limit summation of a Riemann sum, and it became a definite integral. This part can get translated into the integral from a to b. I have here the formula 1 plus the derivative, and I'll just call it regular x now, all squared. And that delta x just becomes my, that's right, dx. So here we have the formula to calculate exactly the arc length. If f prime is continuous on an interval from a to b, then the length of the curve y equals f of x on that interval from a to b is really just the integral of a to b of the square root of 1 plus the derivative f prime of x all squared dx. Da-da-da! Memorize. So, knowing that formula, I'm going to ask you to turn the page, and I've got some examples here where I want you to actually find the arc length. So, what's that formula again? Oh yeah, let's write that down. L equals to the integral from a to b of, yeah, the square root of 1 plus f prime of x all squared dx. Memorize it. So ultimately, you just need to find the derivative, plug it into the formula, and you're good. Thankfully, I hope you still remember how to find derivatives. So for example, number 1, here's my arc length. It's y equals 3x cubed minus 3x plus 2. Yes, please find the derivative, 9x squared minus 3. And then, yeah, just plug it into the formula. The length is just the integral from 0 to 2. The square root of 1 plus 9x squared minus 3, all squared dx. Okay? And if you want to simplify the stuff on the inside, go right ahead and expand that out. So what's that? 81x to the power of 4. Let's see, this is 2ab, so minus 27 times 2 is 54x squared plus 9, and then you got the dx. And if you wanted to simplify even further, go right ahead. 81x to the power of 4 minus 54x squared plus 10 dx. And you're thinking, what integration technique do I know that can help me find this? The answer is, you don't have one. You have to use your graphing calculator to actually evaluate this integral. FNINT, remember that? Function integration? Yep. So I've got the TI-83 func math number. I think it was number 9, was it? Yes, function integration. Here we go. It's the function itself first. So the square root of 81x to the power of 4 minus 54x squared plus 10. We'll close the bracket. Put a comma. The variable's x starting from 0 to 2. Da, da, da. Still thinking. Oh, there you go. 20.633. Yes. Once again, 3 decimal places for the AP exam. And that's the arc length. Okay. So you try number 2. Find the arc length of the portion of the curve of y cosine x from 0 to pi. Remember, y cosine x is just this thing, right? Whee! So I'm going from 0 to pi, which is just up there. So really, what is this arc length going to be? And yep, you can just use the formula. The first thing you need to do is find the derivative. I told you where to start and where to stop. So 1 plus cosine x all squared dx. And once again, this time you cannot do this by hand either. Ugh. So just go ahead and use your graphing calculator. Make sure, because you're using trig, that you are in radian mode. Thank you very much. And then we can go and calculate it now. Once again, it's the square root of 1 plus, and then I like having cosine x in a bracket. Okay, cosine x, close the bracket. Okay, close it, all squared. Close it one more time. So 1 with a square root, comma x, comma 0, comma pi. Let the calculator do its thing. 3.820. Okay. Now these are my examples. If you are using the book and you're looking at Unit 8, you can go there, and yes, it's example number 6. And so really it's the same arc length for the same curve that you did in example number 4, which is just this equation, this one here. So they're asking you to find the length from here to here. Woohoo! And so yes, I'll set up the equation for you, and I'm hoping that you can actually plug it into the calculator yourself to get the answer. It's not that hard. Figure out the derivative, 3x squared minus 1. The length is just from 0 to 2. Once again, 1 plus 3x squared minus 1 all squared dx. And I will just actually not even simplify this. I just plug this into the calculator right now and get your final answer. Okay? And I did this earlier. I think I got 7.414. Okay? You double check. And if you got it, I think you're an expert. Go ahead and try those practice problems and have fun doing them at the same time.